During a complex cardiovascular intervention, a surgical team relies entirely on continuous, real-time vascular imaging. A single second of signal loss during catheter navigation can determine a patient's survival. Historically, angiography was a diagnostic process, taking stationary images to observe blockages. Today, it is an active surgical discipline where physicians perform minimally invasive physical repairs directly inside the blood vessels. Installation is not a simple equipment drop. It requires a specialized build-out that transforms the hospital room into a cohesive, life-saving machine. The engineering must balance extreme competing physical constraints. It must contain massive radiation output, limit vibrations to sub-millimeter tolerances, and support immense transient power draws. The procedure room itself operates as an integrated, life-saving machine. A failure in the surrounding physical infrastructure equates directly to a failure in the clinical intervention. Architectural integration begins with the hot floor concept, centralizing high-acuity services for vascular emergencies. To mitigate transport risks, the suite requires immediate adjacency to the emergency department, operating theaters, and ICU. This substantial footprint demands between 650 and 1,000 square feet. Hospitals must also design these spaces to account for airborne pathogens, integrating specialized isolation architecture directly into the suite's footprint to protect both staff and immunocompromised patients. This is achieved through an anteroom layout, separating the diagnostic and operating spaces. Staff and patients enter through interlocking, touch-free doors, configured so that both sets cannot open simultaneously, maintaining a strict negative pressure gradient. Proper macro placement is the first necessary engineering step. If the suite is isolated from critical care pathways, the most advanced imaging technology in the world cannot reach the patient in time. Once the location is locked, engineers construct the physical shell. The immediate priority is the containment of continuous, high-kilovolt scatter radiation produced during live fluoroscopy. The shielding architecture relies on lead-lined drywall and plywood. Because radiation can leak through microscopic gaps, every seam must be overlapped with thick lead strips, and the control room is protected by massive custom-fabricated lead glass windows exceeding 48 by 36 inches. Beyond radiation containment, the shell must support immense structural loads. The C-arm gantry and the motorized patient table weigh several thousand kilograms, generating extreme static and dynamic stress on the building's frame. This diagram illustrates strict structural tolerances. Under maximum load, floor slab deflection cannot exceed 1/3 of a degree. This absolute rigidity is mandatory. As the gantry rotates, even minor deflection causes mechanical strain, forcing the imaging focal point completely out of alignment with the target. The completed room acts as an impenetrable vault, ensuring biological safety for the staff and sub-millimeter geometric accuracy for the imaging hardware. Beyond macroscopic stability, engineers must mitigate microscopic vibrations capable of blurring high-resolution vascular imaging. To block foot traffic resonance and mechanical interference, the floor structure is engineered to meet specific fundamental frequencies, a minimum of 8.4 Hz vertically and 4 Hz horizontally. Inside the suite, the environmental air quality is aggressively controlled to maintain conditions identical to an open operating room. The HVAC system is specified to perform a minimum of 25 full air changes per hour. It forces this massive volume through high-capacity HEPA filters and seamless stainless steel ductwork to prevent any particulate accumulation. By damping structural resonance and aggressively scrubbing the airflow, engineers create the ultra-stable microenvironment required for complex surgical interventions. With the room prepared, the mechanical installation of the imaging system operates on a tight, highly choreographed timeline, typically executed in 6 to 15 days. On day 0, specialized rigging teams extract the equipment from staging. Heavy components arrive bolted to custom shipping dollies to prevent microscopic internal shifts during transit. By day 2, technicians map the extensive cabling architecture. Thousands of feet of wiring are pulled through dedicated floor trenches and shielded wall conduits, connecting the gantry, generator cabinets, and control consoles. This diagram compares data pathways. Standard copper wiring is insufficient. Fiber optic cables are mandatory to handle massive real-time imaging data. Crucially, fiber optics don't absorb electromagnetic interference. This is a strict requirement in hybrid suites, where heavy MRI magnetic fields would otherwise corrupt the signal. The final mounting phase involves terminating the cabinet connections and locking the heavy C-arm into a reinforced Unistrut ceiling grid, allowing the surgeon 270 degrees of unimpeded physical access to the patient. Successful mechanical integration converts raw construction and created hardware into a high-fidelity imaging device. All this hardware relies on uninterrupted electrical continuity. A sudden power failure while navigating a catheter through delicate neurovasculature is a catastrophic vulnerability. The highest stress on the power system occurs during cine mode imaging, a rapid sequencing of high-dose X-rays used to capture ultra-high-resolution views of arterial blockages. This line chart tracks the power physics of a cine mode sequence. The generator draws a massive transient spike of 100 to 200 kilovolt amperes, compressed into a single 16-millisecond cycle. Older fluoro-only uninterruptible power supplies simply collapse under this extreme inrush current, terminating the procedure instantly. The modern solution is a double conversion online UPS, scaled to provide up to 80 kVA per room. This double conversion isolates the gantry from the utility grid, converting AC to DC and back again. This filters all electrical anomalies and guarantees flawless 1% voltage regulation. During a blackout, the UPS acts as the final failsafe. It absorbs the massive imaging load instantly, holding the system stable until generators spin up. This uncompromising power topology ensures that procedural failure due to electrical artifacting or sudden blackouts is entirely eliminated from the equation. Ultimately, the millions of dollars invested in the gantry and power infrastructure funnel down to a single digital endpoint, the diagnostic monitor at the reporting station. Commercial off-the-shelf displays, regardless of their retail price or marketed quality, are legally and clinically unacceptable for interventional reporting. The hardware baseline requires specialized medical-grade displays with resolutions between 3 and 8 megapixels, providing the exact pixel density needed to accurately render vascular microstructures. These monitors must comply with the DICOM grayscale standard display function, a protocol that dictates immediate and sustained luminance stabilization across the entire panel. To accurately isolate subtle differences in tissue densities and flowing contrast dye, the display must perfectly distinguish up to 256 precise, visually perceptible shades of gray. Because the human eye is far more sensitive to variations in low light than bright light, the hardware utilizes a dedicated lookup table to force a precise gamma 2.2 correction, compensating for our nonlinear visual perception. If this single diagnostic display is improperly calibrated, the entire chain of radiation physics, structural engineering, and power resilience yields clinically useless data. When executed correctly, the multi-ton C-arm gantry rotates in a smooth, continuous arc around the patient, demonstrating flawless mechanical precision. Every frame of data travels from a gamma 2.2 corrected display, back through an EMI-shielded fiber optic network, powered by a double conversion UPS, all anchored to a rigid 8.4 Hz floor slab. Before a single patient enters, the system clears its final administrative hurdle: rigorous commissioning, strict NEMA standard calibration, and independent validation by a licensed radiation physicist. When perfectly engineered, this massive culmination of structural physics, electrical resilience, and digital architecture completely disappears. It leaves only the surgeon, the patient,